talking somatic and autonomic nervous systems. Okay, so thinking back to our first lecture of the unit, we learned about the different divisions of the nervous system. We learned that the two main divisions are the central and the peripheral nervous systems. Central nervous system contains the brain and spinal cord. Peripheral nervous system, basically everything else. Okay. Then we learned that the peripheral nervous system can be subdivided into these two divisions. Somatic, which we see is actually pictured down here at the bottom, is in charge of controlling skeletal muscle, whereas the autonomic, remember that's think automatic, associated with controlling things like the cardiac muscle in our heart, smooth muscle that's found in organs like the bladder that's shown here, and then glands, which I believe this is a salivary gland. And it does so automatically for us. Okay, so we're going to talk a lot about that. We'll kind of start with talking more somatic stuff. And we're going to talk more about the spinal cord. Thinking back to last week, we talked mainly about the white matter of the spinal cord, and now it's like a elevator with sensory or ascending tracks carrying signals up, and then motor or descending tracks carrying signals down. Okay, well, we're going to talk about now the kind of inner core of the spinal cord with its gray matter and how it functions with reflexes. Okay, before we get into specifics about that, I want to just kind of give some anatomy-based stuff so we can kind of understand structure. That way we can then kind of get into more of the functional stuff. Okay. So we'll start by just kind of learning about nerves, which are a big part of our peripheral nervous system. Peripheral nervous system includes those 12 pairs of cranial nerves that we literally just got done talking about, okay, that attach to the brain. Then there's 31 pairs of spinal nerves that arise from the spinal cord, okay. Well, defining what a nerve is, it's a cord-like organ composed of both sensory and motor neurons bound together by connective tissue that can transmit action potentials in opposite directions. That definition is pretty much the exact same thing as what we talked about with the type of cranial nerves that we classified as mixed. Okay, mixed cranial nerves are the nerves of the brain, or connected to the brain, that carry signals into and out of the brain. Okay, well, we just learned that those aren't the only type of cranial nerves that we have. We also have the sensories. We've got the motors that are more like a one-way street. When it comes to these 31 pairs of spinal nerves, they are like a two-lane highway. So they are a mixed type nerve, meaning that they are a two-lane highway transmitting action potentials into and out, or in opposite directions with regards to the spinal cord. Okay, we designate the 31 pairs based on where they arise in the spinal cord. There are 8 pairs from the cervical, 12 thoracic, 5 lumbar, 5 sacral, 1 coccygeal. Okay, this is more anatomy-based stuff. But in some regions, axons from different levels of the spinal cord can come together to form what we call plexuses. These give rise to nerves that can be quite large because they contain axons from multiple spinal cord levels. Let me just really quickly, I know this is anatomy, but I really want to just touch on it real quick, kind of get you visualize on what we're talking about here. Sorry, wrong part. So I'm going to open up a slide here from my spinal cord anatomy lecture. Pictured here, we can see the spinal cord, and all of these branches coming off are the 31 pairs of spinal nerves. You can see there's the 8 pair from the cervical all the way down to the bottom for the sacral and coccygeal regions. Okay, so each of these coming off is a singular spinal nerve, and we've got them on both sides, so that's why we call them a pair. Okay. Over on the left here, we can see what we call the cervical plexus and the brachial plexus. Okay, so like looking here, C5, C6, C7, C8. Notice how, despite the fact that they come off the spinal cord, they actually then come together and they form these kind of complex webbings in certain regions of the body. In the case of the brachial plexus, this is kind of in the upper shoulder. Okay, and then listed here underneath the brachial plexus are the names of various nerves. These nerves here happen to be the nerves that run down and feed our arms. For example, your ulnar nerves are going to go all the way and feed like your pinky and your ring finger. Okay, so that's what a plexus is. Okay, it's just more anatomy based stuff, but I wanted to kind of help you visualize. Okay. So let's talk a little bit more about those spinal nerves. If you look down at the bottom of the page, this illustration should look familiar to you. We saw this same illustration, or at least close to it, the other day when we talked about the spinal cord in our last lecture, when we focused more on the anterior gray, where we learned about the horns. Okay. What we learned in our last lecture were that there are two dorsal or posterior gray horns, and then there are two anterior or ventral gray horns. Now, those are associated with what we call the roots of our spinal nerves. Okay. Just before connecting to our spinal cord, each of those spinal nerves forks. One fork goes to the front of the spinal cord, one goes to the back of the spinal cord. The one that goes to the back of the spinal cord, we call the dorsal or posterior root. Okay. And inside of that dorsal or posterior root are sensory neurons. Now, we only show one here in blue, but keep in mind, you're probably going to have thousands, if not more, in each of these roots. Okay. Which means that the dorsal roots always got signals going into the spinal cord where they synapse in that posterior or dorsal horn, okay, that we talked about last time. Okay. On the other side is what we call the ventral or anterior root. Okay. And inside of there are the axons of motor neurons. Okay. Specifically, in most places, it's just the somatic motor neurons that are in that root. Okay. But we also learned previously that in a little bit of our spinal cord, about half of it, I should say, I think it's like between T1 and L1 or something like that, you're going to find these lateral horns, okay, which is where you find the gray matter, or excuse me, in the gray matter is where you find the autonomic motor neuron cell bodies, which also travel out from the spinal cord using those anterior roots. Okay. Now, if we look here, we see this somatic motor neuron. It can be stimulated directly by an interneuron. We talked a little bit about how the spinal cord connects as a reflex center. But when we do most of our muscular contractions, and when I say muscular contraction, I'm talking about skeletal muscle contractions, like as you guys are writing your notes or as I'm moving my hand to move the cursor, that signal's not beginning in the spinal cord. It's actually beginning back up in the motor areas of my brain, okay, or the motor areas of your brain. Okay. Specifically, that primary motor area of the cerebral cortex, which is one of those functional areas. Okay. So that signal originates at the very top of our brain using what we call upper motor neurons that carry a signal down and then stimulate these guys, which go the rest of the distance out to the skeletal muscles. And we generally will call these what we call lower motor neurons. Okay. Lower motor neurons are the somatic motor neuron, or would be this one that you see here. Okay. So that's pretty complex stuff, but I wanted to kind of get into it just briefly. Okay. So when connecting to the spinal cord, those spinal nerves branch. As soon as they leave the spinal column, they then branch again. And that's what I want to talk about here, what we call rami, which is just a plural form of the word ramus. Okay. A short distance after traveling through its intervertebral foramen, which is just like the hole that allows the spinal nerve to leave the column. Okay. And these spinal nerves, you can see, come out and then fork again. So they're forked, connected to the spinal cord, come together as one spinal nerve, and then back out here, they fork again. Each fork is called a ramus, and there are a few different ones. The most important of the two are the posterior and the anterior ramus. Looking at the size difference here, posterior ramus is quite a bit smaller than this big anterior ramus. Okay, and that's because the posterior ramus, which goes to the back of the body, only innervates the muscles and skin on the posterior surface of your head, neck, and trunk. So basically the back side of your head, the neck, and then your back, what we typically call to, like, you know, about the level of our butt. Okay. Doesn't include your arms, or your legs or the front or sides of your body. Okay, innervating those are the nerves that eventually come off of what we call the anterior or ventral ramus. Okay, so they serve the muscles and structures of the upper and lower limbs, so our arms and legs, and the skin and lateral of the lateral and anterior surfaces of our trunk. So most of the nerves of the body come from these anterior rami. Okay, it's these anterior rami that form those plexuses, those branches or webbings that I was showing you from my anatomy lecture. Okay, so now that we've kind of got the anatomy-based stuff out of the way, we can really turn to now talking about what those cranial nerves, what those spinal nerves can do as far as reflexes go. I kind of got into this just briefly the other day, but as I mentioned, we kind of focused more in that last lecture about the white matter of our spinal cord and how it can carry signals up and down. We talked about those different tracks, ascending, descending, or sensory motor. Let's talk now about how our spinal cord can promote homeostasis by serving as an integrating center for some reflexes. Okay, and I say some reflexes, not all reflexes. If the integration does take place in the spinal cord's gray matter, we would call it a spinal reflex. Okay, the other day I mentioned the patellar tendon reflex, like when you sit on the table at the doctor, they tap on your patellar tendon, your leg kicks out. Okay, the spinal cord does the integrating. It processes that information and decides what to do with it. Okay, thinking back to the video that we watched the other day of action potentials, and we saw the little girl at the beginning of the video touch something hot. Okay, the response that our body has, or the reflex that our body has to when we hurt ourselves, like touching something hot, is another example of a spinal reflex. We'll look at some of those here in the next couple of slides. Okay, most reflexes, though, that we actually talk about this semester are cranial reflexes, and this is where the integration occurs in the brainstem rather than in the spinal cord. So it's much more complex, okay, and it's going to be, reflexes related to like digestion, urination, that kind of stuff. Okay, most of those reflexes are cranial reflexes. Now, no matter what the reflex is, whether it's spinal or cranial, we can describe it as being quick, so it happens almost instantly. Okay, and once again, demonstrating that we're always dealing with milliseconds when it comes to the nervous system. It's involuntary, meaning that we are occurring, or this is going to occur without our intent, often even without our awareness, and it's very difficult to suppress. Okay, well, like going to the doctor and them tapping on your patellar tendon, you are aware that's happening. Okay, but when we do reflexes related to like your blood sugar and your breathing rate, your pH, we generally don't even understand or know that that's happening. Okay, so that's what I say when I'm saying, that's what I mean when I say it's occurring without our awareness. Okay, and then it's hard to suppress. Does it mean it's completely impossible to suppress reflexes? No, like preventing yourself from peeing your pants is a way to suppress a reflex. And we can suppress some, but not all of them. Okay, and they're stereotyped, meaning that they are essentially going to occur the exact same way every time, and the response is very predictable. If you've ever seen like the old school TV show, The Three Stooges, or they made a movie not too terribly long ago, it was probably 15, 20 years ago. The guys that are like always hitting each other, making weird noises. I always think of the, I don't know if it's a true episode or it's a cartoon, but I always think it's this Three Stooges. Doctor goes, puts the guy on the table, taps on the patellar tendon. Instead of kicking his leg out, what would have naturally happened? The guy punches the doctor in the face. Okay, that's not what happens. Okay, reflexes don't just like randomly, things are not just randomly happening. We know exactly what's supposed to happen, and it's very predictable. Okay, so why do doctors test for reflexes? Well, sometimes they don't happen. Okay, it's not like something different happens, like punching the arm instead of kicking the leg, but sometimes reflexes don't actually occur, which is going to tell the doctor that something's not right. Okay, could be something in the spinal cord, could be something up in the brain. Something's not happening the way that it's supposed to. So this is another one of those, pieces of information used for diagnostic purposes. Part of that, physical exam that we've talked about previously. Now, with regards to reflexes, and it's relating back to the very beginning of the semester, when we talked about things like sweating and shivering, we don't just do these things and we don't just have reflexes occurring willy-nilly. Okay, they all require some stimulation. They're not spontaneous actions, but responses to sensory input. So it all begins with an input and a response occurs. So the input for like shivering is body temperature drops. It's cold outside. So what do? As a response, we shiver. Okay. Make sense? Okay. I'm kind of going to do this backwards. It's just the reason being that the textbook and the publishers that make the textbook do it this way. We'll talk more about sensations in our next lecture, our next unit. Okay. What we'll focus in more on this lecture is the motor signaling, and that's what somatic autonomic really is. Motor signaling going out to places like our skeletal muscle for somatic, or cardiac skeletal or cardiac smooth and glands for autonomic. Speaking of autonomic, somatic, we can use those terms to describe reflexes. Autonomic or visceral reflexes consist of contraction, and it really should say, or relaxation of our smooth muscle or our cardiac muscle, because it's not always that we want to contract. Sometimes we want to relax. Like if we want to dilate a blood vessel, we have to relax the smooth muscle. Okay. Or it could be secretion by a gland, or really it could be inhibition. So not secreting by a gland. Okay. We'll discuss these more towards the end of the lecture. Okay. I typically call them autonomic reflexes, but this you can see there, the term visceral is also used from time to time. And that's because the word viscera or visceral just refers to internal organs. So things like your heart, where the cardiac muscle is, your stomach and intestines, where you're going to find smooth muscle, the bladder, etc. Okay. Those are the most complex of our reflexes. Things we're regulating like blood pressure and heart rate, digestion, urination, okay, sexual responses, and so on and so forth. We'll spend a lot of time this semester talking about those as we go through those different systems and learn about those different processes. Okay. Our next couple slides, I'm going to talk about some of our specific somatic reflexes. Okay. And since we're talking somatic, we're going to involve skeletal muscle. Okay. We're going to contract or relax skeletal muscle using what we call a reflex arc. And a reflex arc involves an action potential arcing into the gray matter of our spinal cord using a sensory neuron. We show one here in blue. And then out of the spinal cord using a motor neuron shown here in red, traveling to our skeletal muscle, which is going to the effector. Okay. A reflex arc signal is going to travel in the following pathway. And you're going to want to know these 5 different parts to a reflex arc. And you're going to want to make sure you know the order. It begins with a sensory receptor, which in many cases, and shown right here, is just the dendrites of a sensory neuron. Okay. And in this case, looks like the sensation is probably going to be pain, because it looks like a tack has been inserted into the skin. So maybe the person stepped on a tack or a nail or whatever. Okay. Something that we don't like to do, but it does happen from time to time. That sharp object cuts into the skin, triggering those dendrites, which are the receptors. And in doing so, this creates a strong enough depolarization that an action potential or multiple action potentials are going to propagate along the number 2 sensory neuron using the backside of the spinal cord, using what we call the posterior or dorsal root of our spinal nerves that comes into the posterior or dorsal gray horn that we previously talked about. Okay. Synapse occurs with what we call an interneuron, where we integrate. Okay, integrating center in the case of a spinal reflex, which is what we show here, is going to be the point of synaptic contact between neurons in the gray matter of the spinal cord. If this was a picture of the brainstem, it could also be doing the integrating if that was a cranial reflex, but this happens to be a spinal reflex. Okay. These synaptic events determine whether the output or efferent neurons issue a signal to the muscle. Okay, and if so, that is going to result in activation of motor neurons, which carry the signal out from the front of the spinal cord, originating in the anterior or ventral horn, and then travel out thanks to the anterior or ventral root of our spinal nerve, and eventually go all the way to our effectors, which are going to be skeletal muscle when we're talking somatic. Okay. Now we'll see a similar illustration at the end of the lecture with regard to autonomic reflexes, except a big difference is the effectors for autonomic will not be skeletal muscle, but instead will be cardiac muscles, smooth muscle, and glands. Okay. And in the case of most autonomic reflexes, it's not the spinal cord that's going to be doing the processing or the integrating. It's going to be up in the brainstem. Okay. So we'll get to that. But for now, let's just talk about somatic reflexes, and we're going to call them somatic spinal reflexes. So we're talking effectors being skeletal muscle, somatic, and information processing, the integrating, is taking place in the spinal cord. The first reflex is that same reflex I've been talking about here for the last couple of days. That is done when we go to the doctor and they have you sit on the table, dangle your leg down, and then they tap on it with a what we call tendon hammer. And in doing so, the response is our leg kicks out. A patellar tendon reflex or knee jerk reflex is what you'll sometimes see this described as. Okay. It doesn't always have to take place at the knee. Okay. This can also take place at basically any joint where you've got tendons. So places like the elbow, the wrist, and ankle as well. So you could do it, on the back of the ankle to the Achilles. That'd be an easy one to do it as. Okay. But the actual name for this reflex is called the stretch reflex. And that's because it occurs in response to stretching. So that's the original stimulus. The muscle is stretched, and as a result, that same muscle contracts. Okay. So let's kind of describe it in this illustration. Hopefully we'll make some sense after we run through it. Okay. So it all begins by tapping on the patellar tendon. You can actually tap on this tendon just above the kneecap, what's called the quad tendon, because they're actually connected to one another. That's not really that important to know. But basically, by tapping on that patellar tendon, it causes the quad muscles to stretch. Obviously, it's not going to be a huge stretch, but it is enough of a stretch to stimulate what we call muscle spindles. Muscle spindles are the receptors or sensors, what do you want to call them, that wrap around the muscle fibers, and their job is to monitor how much stretch the muscle is currently under. Okay, so when that muscle is stretched, the spindles are activated. They then create an action potential that then travels into the backside of the spinal cord, where then we see a couple things happening. Okay, first of all, we're going to involve signals traveling out into the white matter to go up to the brain so that we can actually feel and be aware, or have that perception of that touch of that tendon to our foot or to our knee. Okay, not to our foot, to our knee. Okay, while that's occurring in the gray matter, what's more important here in the reflex is what takes place right here and here. Okay, we're going to end up synapsing with two different motor neurons. Okay, one we see is a positive, one is a negative. The positive symbol is an excitatory signal. The negative symbol represents an inhibitory signal. So what happens is an excitatory signal triggers action potentials that travel back to that same muscle that was stretched. Okay, and as a response of that excitatory signal, the muscle contracts. Okay, now while that's occurring, we're sending inhibitory signals to the antagonistic muscles, causing them to relax. So these muscles cannot contract, which is good, because if they contract at the same time these contract, they're just going to counteract each other. So by relaxing the hamstrings, contracting the quads, the leg kicks out. Okay. We call this type of reflex a monosynaptic reflex arc because it only involves one synapse crossing the central nervous system, okay, which is really not that big of a deal, nor is like all this information. That's why I didn't really read it all. Main thing you want to kind of focus on is just like the definition up here at the top and what's happening. Also make sure you know that muscle spindles are the receptors, in this case, for a stretch reflex. Now, the exact opposite of that reflex is what we call the tendon reflex. The tendon reflex is a feedback mechanism that controls muscle tension, so not stretch, but tension, caused by, or by causing, it's not caused by, but by causing muscles to relax before muscle force becomes so great that tendons might be torn. Okay. So in our illustration here, we're still using the same joint, the knee, okay, and we're still using the same muscles, the quads, the hamstrings, okay. This time, we're going to begin right here with these receptors called Golgi tendon organs, or as they're just listed as tendon organs. Okay, these are end tendons, and their job is to detect changes in muscle tension or force caused by passive stretch or muscle contraction. Okay, so basically, what's taking place in this is the quad muscles are contracting forcefully. Okay. And that's going to trigger these guys to create an action potential. Okay. So the tendon, by being pulled on by the muscle, is under a lot of stress. Okay. So that's what activates them. They send a signal into the back of the spinal cord. We see the kind of same thing. Some signals go up to the brain, but more importantly, what's taking place is here in the gray matter, where we now kind of see the same thing happening, where a signal is going out to the quads and a signal is going out to the hamstrings. Except it's the exact opposite as what we just learned for the stretch reflex. Okay. The excitatory signal is going to end up going to the antagonistic muscles, causing them to contract. And the inhibitory signal is going to go to that same muscle that was originally contracted, the quads, which means they relax. And in doing so, the leg pulls backwards, which is going to relieve all the stress off of that tendon. Okay. So this is a protective mechanism to prevent tendons from being torn when the muscles are contracting very forcefully. Now you might be wondering, like, how do we lift weights or pick up anything that's super heavy? Okay. We actually have to kind of suppress this reflex if you want to do that. Okay. Because if you could not withstand this reflex, you would not be able to do anything like as far as like lifting heavy objects. Okay. Because that would cause the muscle just to relax when it starts contracting forcefully. So it's a rare instance where you can actually suppress a reflex. And I kind of already mentioned that it is possible sometimes, just not all the time. Okay, our last two somatic spinal reflexes I want to talk about, we'll talk about them together because that's important. They go together. The first one is that same reflex we've been talking about and was also in the video that we watched where the little girl touched the hot stove or the hot pan, whatever it was. We call this the flexor withdrawal reflex. So it's a reflex that allows us to withdraw a body limb in response to something painful. Okay. Like in the illustration here on the next page, stepping on a tack. Okay. Stepping on a tack, obviously, is going to be a painful situation. Pain sensitive receptors in our toes are activated by that tack entering the foot. A signal is created that then travels up and into the backside of our spinal cord. Okay. But notice here we've got 3 segments of the spinal cord shown, and that's because this is a intersegmental reflex arc. Okay. Just super complicated, but basically it just means that we're going to use multiple spinal cord segments. Okay. What that means is when that signal comes into the back of the spinal cord right here, we're going to also see synapse occurring with interneurons that carry the signal up and down using the white matter so that we activate not just one segment of the spinal cord, but multiple. Remember, inter means between, so intersegmental means between segments, okay? Well, no matter what part of the figure you're looking at, okay, the ultimate result from all three segments here is an excitatory signal that goes to the back of the leg to what we call the hamstrings, which are the flexor muscles. And as a response, the leg flexes, the knee bends, and the toe gets removed from that tack. So we flex the knee to withdraw it from the pain. Okay. Now, while that's occurring maybe with the right leg, we're going to have to do something with the opposite side. In the case of the right leg, it'd be the left leg, so that when we pull our leg away from that tack, we can then shift our body weight to the other side. And that's what we call the cross extensor reflex. So this is going to cause contraction of muscles extending joints in the opposite limb in response to a painful stimulus. So here on the following page, we put it all together. Okay, if I draw a line basically down the center of this picture, from here, center to the left, this is the flexor withdrawal reflex. Just the exact same thing that was on this previous page. Okay. From the middle part across to the right side is the cross extensor reflex. Okay. So we'll just start where we started with just a second ago. Stepping on the tack stimulates receptors in the toe, signal comes up and into the spinal cord. It goes up, it goes down, signals go back out to that same leg, to the flexor muscles, the hamstrings, and you withdraw the leg. Okay. So if you bend your right leg away from the tack, or if it was in my house, a Lego or an army guy, if I bend my right leg as I'm standing up, I need to make sure that I don't fall over by shifting my body weight to my left leg. Okay. Which means that my left leg must be straight to catch my body before I crumple over to the ground. So going back to here, the signal comes into the spinal cord. Not only does it go up and down on that same side, but thanks to the fact that there's that crossbar to the gray matter, we then cross over to the other side of the spinal cord, go up and down, just like on the other side. And then excitatory signals come out from those multiple segments that go to the extensor muscles, the quads of the left leg. So the leg is straight. That way, when we shift our body weight, we can step onto the left leg and not just fall down because we've bent our right leg. We can't have a bent left leg too, where we would just crumple over. So thinking back to last week when we talked about all those steps of an action potential, all those ions flowing in, out, depolarization, repolarization, voltage gated sodium channels, voltage gated potassium channels. Okay. Talked about saltatory conduction, continuous conduction, where the signal travels down the length of the axon. And we talked about the 7 steps of a synapse. Okay. Just look at how crazy something that we experience fairly often. Hopefully you're not stepping on tacks all the time, but we step on stuff that hurts quite a bit. We touch things that hurt quite a bit, hopefully not a ton. But look how many different neurons are involved with something that we experience fairly often. Okay. Look where we see neurons meeting. Anytime you see these little dots, that tells you got a cell body. On the other side is axon terminal. So this is a synapse, another synapse, another synapse, another synapse. We got neurotransmitter release happening all over the place. Why I kind of bring that up is because you can't really appreciate your nervous system and how amazing and complicated it is just by thinking about what you know and have learned. I don't know what I can do to make you, geek out as much as I do, because it's amazing. Okay, let's move on from reflexes. All right, what we're going to do now is really kind of change gears to more talking about the autonomic nervous system. We've spent the last few slides talking more somatic than autonomic. Let's get into more of the autonomic stuff. As previously learned, two divisions of the peripheral nervous system are somatic and autonomic. And just a review of what we already know. Somatic is defined as the motor nervous system that controls skeletal muscle. Things like those reflexes that we just talked about involve the somatic nervous system. The much more complicated division is the autonomic nervous system, which is associated with motor control of our glands, cardiac muscle, and smooth muscle. And as I told you guys previously, when you hear the word autonomic, you can think of automatic because it usually carries out its actions involuntarily without our conscious intent and awareness, which is typically in contrast to the voluntary nature of our somatic nervous system. Okay. Now, back in that first lecture of our nervous system, we also learned that we can subdivide the autonomic nervous system to three divisions: sympathetic, parasympathetic, enteric. Okay. We're not really going to talk enteric at this point. We'll wait and talk more about it when we get to the digestive system, because that's what it regulates, digestion. So we're going to focus here for the next several slides about the sympathetic, parasympathetic motor neurons and what they do, along with the brain regions that regulate their activities. Okay. As we know, sympathetic produces the fight or flight response, whereas the parasympathetic produces the rest and digest response. Okay. Thinking about our various organs of the body, I just typically kind of just think about the heart. It's pretty obvious to know what like the sympathetic is going to do to the heart. It's going to make it go faster. It's going to make it beat faster. It's going to make it beat stronger. Okay. Whereas the parasympathetic is going to make it beat slower, and it's not going to beat as hard. Okay. Well, the two divisions of our autonomic nervous system have a property known as dual innervation, meaning that they have contrasting effects on that same organ. Okay. So like I was just saying, sympathetic makes it go up as far as heart rate goes, parasympathetic makes heart rate go down. Okay. So dual innervation means that organs are innervated by both systems, and that these two systems have contrasting effects. One makes something go up, one makes it go down. Okay. Now, just like with those reflexes that we just talked about, whether that was touching something hot, stepping on a tack, tapping on a patellar tendon, okay, responses like changes to heart rate, to blood pressure, to secretion of a gland don't happen without first input, some type of stimulus changing the body in a way, okay, that triggers what we call autonomic sensory neurons. Okay. Autonomic sensory neurons are primarily associated with interoceptors, which we call interoceptors because they're located in our interior, places like our blood vessels, where they monitor like blood pressure and blood acidity and oxygen levels in the blood. We also have them just in our visceral organs, so places like in the stomach and intestines and whatnot. Even our muscles have receptors, and even our nervous system has its own receptors monitoring conditions. And when it's the interoceptors, we're always talking about the internal environment. Okay. As I told you earlier, we're going to talk more about sensory stuff, and so we'll talk more about interoceptors in our next lecture, not today. Okay. But I wanted to kind of emphasize that we don't have activity sympathetic, parasympathetic without first having a change, an input signal triggering that response. Okay, we can say that autonomic motor neurons regulate the visceral activities by either increasing, which we could just replace that word with exciting, or decreasing, and we could replace that word with inhibiting the ongoing activities in their effector tissues. And when we talk about autonomic nervous system, the three effectors are always going to be cardiac muscle, smooth muscle, and glands, as we showed down here at the bottom. Now, as opposed to somatic motor neurons, which once again are the ones that control our skeletal muscle, and they're also usually myelinated, they're going to travel all the way from the central nervous system to the skeletal muscle fibers that they innervate. In the case of autonomic nervous system motor pathways, we're going to use two motor neurons in series before we get from the central nervous system to the effectors. If I go back to that very first picture, two pictures on the front page, this is illustrating those two different divisions. Somatic is at the bottom, autonomic is on top. Okay, I can tell you for a couple of different reasons. Well, if you just look at the effectors, who's at the end, in the case here, we've got cardiac muscle, heart, smooth muscle in the bladder, and a gland. This has to be the autonomic nervous system. Down here, this is a skeletal muscle, so we know this is somatic. Okay. Another easy way to tell that they are different is by just looking at the number of neurons it takes to get from the central nervous system, in this case, the spinal cord, to the effector. If it's somatic, it's always one neuron going all the way to the muscle. Okay. So when you do your note taking and contracting the muscles in your forearm, that signal that's causing those muscles to contract in your arm, the neurons that trigger that are originating in the spinal cord and then traveling all the way through your arm and into that muscle, whatever, wherever that is, forearm or into your hand. But if the signal is going to things like our cardiac muscle, our smooth muscle, our glands, it takes two neurons to get there. The first neuron is called a preganglionic neuron. The second neuron is called a postganglionic neuron. And we call them that because where they meet is called autonomic ganglion. And that says point of contact, but keep in mind, remember, neurons don't literally touch. It's where they're almost touching, where what we call the synaptic cleft is. Hopefully by now you know that pre means before and post means after. If you didn't know that, now you do. So the preganglionic neuron comes before the ganglion. The postganglionic comes after. Okay. And so the preganglionic comes out of the brain or spinal cord. In this case, we show spinal cord. It then synapses, releasing neurotransmitters that activate the postganglionic neuron, and the postganglionic neuron then travels to the actual effectors. So we still get there, it just takes a couple extra steps because we've got two neurons to get there instead of one. Now, illustrated here are those two divisions of our autonomic nervous system that we'll talk about. Here at the top is the parasympathetic, down at the bottom is the sympathetic, which we'll talk about significantly starting now. Okay, let's start by talking sympathetic. Once again, this is what produces the fight or flight response, so we can call it the fight or flight division because it adapts the body for physical activity. Okay, could be as drastic as running from a bear or fighting a bear if we come across it. Hopefully nothing that we ever have to experience. Could be as simple as what happens whenever you are physically active, as simple as like just going for a walk or, playing a game of basketball and hopping on a treadmill and running, whatever. Okay, it's going to trigger things like increases in heart rate, blood pressure, pulmonary airflow, blood glucose levels, blood flow to cardiac and skeletal muscle. Okay. Now, with regards to signaling for the sympathetic nervous system, it all comes from spinal nerves T1 all the way down to L2. Okay. So in other words, and we can see here on the right side of the next page, all signaling for the sympathetic nervous system involves kind of the middle part of our spinal cord and the spinal nerves associated with that. Okay. When those signals leave the spinal cord, Most of the time, that preganglionic neuron, the first neuron, travels out in synapses with the second neuron in what's called a sympathetic trunk or chain of ganglia, whatever you want to call it, okay, which is on both sides. This picture is only showing it on one, but there are two of them, one on each side. Okay, if I go ahead a couple slides here, we can see where we have a figure of both of them. Okay. Typically, that first neuron comes into the chain, which is just going to travel up and down the spinal column. What we can see here is the spinal cord and those two trunks or chains, whatever you want to call them. Keep in mind that we wouldn't be able to see the spinal cord if the spinal column was there. If all those vertebrae were included, we wouldn't be able to see the spinal cord inside. Okay. So the spinal column, all those vertebrae would be in this area, and the two trunks are on both sides. Okay. Most of the time, that first neuron comes out and synapses here. Okay, we can see that all over the place up here at the top. If you see all these little blue dots, that's the cell body of the second neuron. Okay. Well, since the first neuron typically only goes out of the spinal column to those two chains, the first neuron of the sympathetic nervous system is typically very short. Okay, the preganglionic neurons are usually short, and then traveling to the target organ, we typically have long postganglionic fibers. And if I go back to this page, we can see that. Okay, the first neuron is shorter than the second neuron. It doesn't really do it great justice, but it is shorter here and then longer here. Okay, we see the opposite for the parasympathetic. It goes long and then short. Okay, and you'll find out why that is. Now, since the sympathetic nervous system uses just the lumbar and the thoracic parts of our spinal cord, another nickname for the sympathetic division is what we call the thoracolumbar division, which I am going to want you to know. Okay, thoraco for thoracic, lumbar for lumbar. Okay. In the case of the parasympathetic division, which produces that rest and digest response, it's going to calm your body down. It's going to assist in maintaining what we would call resting homeostasis. So things like maintaining a resting heart rate, performing digestion, eliminating waste. The signaling for the parasympathetic comes out of our brain using 4 pairs of cranial nerves, plus a little bit down there at the bottom of our spinal cord, down there in the sacral region. It does not use the majority of the spinal cord at all, just a little bit at the bottom. And then up here, we can see these Roman numerals telling us that we're dealing with cranial nerves. Okay. Notice that we don't include the chains that we saw here. That's because there is no association with those two chains or trunks for the parasympathetic division. Okay. And since we're talking about the parasympathetic using the cranial nerves and the sacral region of the spinal cord, the other term to describe your parasympathetic nervous system is the craniosacral division, which I'm going to want you to know. Okay. So thoracolumbar, nickname for the sympathetic; craniosacral, nickname for the parasympathetic. Now, back a couple class periods ago, I mentioned and I kind of described the relationship between these two divisions like that of a teeter-totter, where if one side is up, the other side is down. Okay, that balance between those two divisions has a fancy term. We call this autonomic tone. It's the normal rate of activity representing the balance between parasympathetic and sympathetic activity. Right now, I look around the room, I look on screen, I see illustrations of parasympathetic activity. You're not breathing rapidly, you're not sweating, your face isn't flush red, okay? You're resting, okay? But keep in mind, these two divisions, like a teeter-totter, can drastically flip sides. Okay, if I told you guys, let's take the test now instead of waiting till the next class period or till next week, okay, you might experience a fight or flight response by wanting to run out of the room, wanting to fight me. Okay, Your heart rate's going to go up. You're going to start sweating. You're going to start breathing. Blood pressure is going to go way up. Thankfully, I'm not going to do that to you. Okay. So that's autonomic tone. Okay, now looking here on this next page, which I've kind of skipped over once already, we see a comparison on at the top, somatic, which I would highlight that this is the somatic. And I can tell you that not only because it's labeled, but we see the signal coming out of the spinal cord, traveling all the way to our skeletal muscles, which are the effectors. One neuron going a whole way. The second two figures, so figure 2 and figure 3, connect those with a bracket or draw a line to them and label those as the sympathetic nervous system. The bottom picture, label that as the parasympathetic nervous system. Now, the second figure and the fourth figure are basically the exact same thing as these two figures that we saw a couple slides ago. For the parasympathetic, we just learned it's a long pre and a short post. In the case of the sympathetic, it's a short pre and then a long post. Okay. There is a fourth picture, and it's this one right here that is included to demonstrate that something also takes place whenever the sympathetic nervous system is active, and that's going to involve what we call the adrenal medulla. So let's find out about that here on this slide. Most of this kind of stuff at the top I've already kind of gone through, but I'll read through it again. So most preganglionic neurons in the sympathetic division synapse with postganglionic neurons in the sympathetic chain of ganglia. So once again, most of the time the first neuron comes out, it then synapses with the second neuron, then from there it goes out to the effectors. Okay. Now, what we can see, especially like down here, is that thanks to the fact that these preganglionic neurons a lot of times have axon collaterals where they have a kind of a left turn, they're able to go up and down the chain, kind of like an elevator. So that enables them to synapse at different levels of the chain. Okay, instead of just being like right here, etc., they can go up and down. Okay. In our abdomen, sometimes the signal is not going to be synapsing, or the two neurons aren't going to be synapsing inside the chain. Instead, they synapse with postganglionic neurons in what we call collateral ganglia. You can see those are the kind of ovals that we see down here. The same sequence of events as what we saw like up here. First neuron synapses with the second neuron carries it, and that signal to the rest or to the organ. Okay. The one exception to this basic sequence involves what we call the adrenal medulla, which is essentially an extension of the sympathetic nervous system. Okay. We're going to talk more about the adrenal medulla in our next units. It is the middle part of our adrenal glands. We have two adrenal glands. They sit on top of our kidneys, like little top hats. Okay. There's two parts to each adrenal gland. The adrenal cortex is on the outside. We'll talk later about what it does. Let's talk about what the adrenal medulla does. It's the middle part of the organ. Inside of the adrenal medulla are these cells called chromaffin cells. Okay. Chromaffin cells become activated by those preganglionic neurons of the sympathetic nervous system, just as if they were part of the sympathetic chain of ganglia. So in other words, like I said, the adrenal medulla is just like an extension of the sympathetic nervous system. It's just like what was happening here when the two neurons meet outside this adrenal medulla. Now, in response to sympathetic activity, those chromaffin cells of the adrenal medulla secrete three chemicals into the bloodstream. Okay, mostly it's epinephrine. About 80% of what it dumps into the blood is epinephrine. And as we learned last week, adrenaline is what we commonly call epinephrine. But you also are going to dump in norepinephrine, about 20%. And then it's not even included because it's so small in amounts. So that's why you don't see it in this figure. We also dump in dopamine. Okay, but it's just so small, it's what we would call a trace amount. Okay. But the function of these chemicals is to act as hormones carried throughout the blood, where they can then circulate to basically any cell that gets a blood supply to intensify the sympathetic fight or flight response. In other words, it helps distribute the adrenaline to cause that adrenaline rush that you experience when your sympathetic nervous system's active. Okay. So that's going to make things like elevating your heart rate, your blood pressure, making your heart beat harder, breathing rate intensifies, and it makes that really widespread throughout the body. As we'll find out, a lot of things happen when that sympathetic nervous system is active. Okay. So whenever you have the fight or flight response active, not only are you using neurons and releasing neurotransmitters, you're also dumping hormones from the adrenal gland into the blood. And so that's why this picture was on the previous page. Now, unlike the sympathetic nervous system, the parasympathetic nervous system does not have ganglia in a chain. So that's why we don't see those two chains in this picture. Instead, the synapsing takes place out in what we call terminal ganglia, which in many cases, like right here, is almost actually within the organ that's being served. Okay. Where the first neuron and the second neuron meet is almost at the organ or even within the organ that's being served. Okay. That's why it's a long pre and then a short post. Okay. As far as the parasympathetic nervous system, most parasympathetic activity comes courtesy of those vagus nerves that I introduced to you guys in the last lecture. Okay. They carry out nearly 80% of total parasympathetic nervous system outflow. So about 80% of your rest and digest signaling comes thanks to cranial nerve pair number 10. Okay. Remember I told you guys vagus does not mean Las Vegas in this case, it means wandering, because these nerves originate in our medulla, and look where they go and innervate, as far down as our intestines, stomach, spleen. So they have to go through the neck, through the chest, down to the diaphragm and into the abdominal cavity. So they innervate a lot. I mean, look at all these branches. Goes to the heart, goes to the lungs, goes to the liver, all those intestinal organs and stomach organs. Okay. Now, as you can see, the vagus nerves are just one of 4 pairs that innervate us for the parasympathetic nervous system. The other pairs are 3, 7, and 9. Okay. Collectively, those other 3 pairs don't go down and innervate things like our intestines. They stay more up towards our head, which should make sense because, you know, your brain's up there by your face, right? So these nerves stay kind of where they originate, okay? Innervating things like your eyes and your lacrimal glands, which produce our tears and so on and so forth. Okay? Now at the very bottom of our spinal cord in the sacral region, we use the sacral parasympathetic outflow to innervate our most inferior pelvic organs, things like our urinary organs like the bladder and reproductive organs. Here's a male reproductive system, here's a female reproductive system, okay? Along with other structures like the colon, which is, you know, down there as well, but just not shown. I guess it is right there. So once again, demonstrating the craniosacral division as opposed to the thoracolumbar. Now, going back to that thought of, go back to it, what is it listed as? Dual innervation. How the heck does our heart, for example, know to speed up when the sympathetic nervous system is active? How does the heart know to slow down when the parasympathetic is active? It has everything to do with neurotransmitters. Okay, we're going to stop here. This is a perfect spot to stop. We'll pick up with neurotransmitters on Thursday. And we are going to be able to finish up that without too much trouble. When we're done on Thursday, we'll start our next unit on the sensations lecture, which won't be on the exam. The exam will be next Tuesday. But what's nice about that sensations lecture, it is nervous system stuff. So we're still in the same system. We still are talking about action potentials, all that wonderful stuff. So it's not like we're totally switching gears and confusing your brain even more. Okay.